Quantum networks are the underpinning piece to scaling both compute and sensing, regardless of who you are. This is a technology that will touch your life, and it will do it for the better.
This is Deep, the show about the emerging deep technology that will change the world. Today, I'm chatting with Prineha Narang. You can call her Pri. She's a highly regarded quantum scientist shaping how quantum computing, networks, and sensing move from lab demos to real-world infrastructure. Pri currently serves as a UCLA professor in electrical and computer engineering, and her research team at UCLA co-designs algorithms and hardware for near-term quantum devices, works on advanced methods to boost quantum sensor sensitivity, and also explores how quantum computing can co-inhabit data centers along large-scale AI. So what does it mean to plug quantum into a modern data center? Which cross-disciplinary bets in quantum, say drug discovery or new materials or bioaerosol diagnostics, hold the greatest promise? And how soon will quantum networks deliver physics-grade security and impactful new applications to homes and entire cities? I'm Ben Kaplan with Deep Venture Partners. As always, our email is deepshow@deepvp.com. And let's go deep.
When I think about quantum science and technology, it spans compute, network, and sensing. And to me, those are the three pillars that are really driving the field today. So within quantum mechanics, right? So if you pull a quantum mechanics textbook, classical treatment of quantum mechanics would say, okay, there are things we can realize quantum mechanically that have no classical analog, right? And that includes superposition, that includes entanglement. The underpinning idea with these technologies is how do we use those quantum-only resources to compute better, to network better, and to sense better? So in some ways, the fundamentals of quantum mechanics are truly what are enabling all of these technologies. And it's the International Year of Quantum, yay! And we celebrate both the fact that the foundations of quantum mechanics, the advances in the various pieces of quantum mechanics, theoretical and experimental, have brought us to a point where we're talking about truly a technology, a scalable technology across these three areas.
So classical computing, anyone who studies the basics of computing is that, okay, this is based on, bits, binary, 0 or 1. Quantum computing sort of says it's a lot messier than that, and you can hold multiple states at the same time. The states influence each other. How does that notion of it start to change the way we understand that computing works?
So in quantum computing, we're using qubits and not bits, and how we control these qubits, how we prepare, address, how we use them in various quantum algorithms is fundamentally different. So the question we can then ask is, if we say have some entanglement across some number of these qubits, we can do very, very controllable gates. What is the computational capacity of such a system? And that's a fundamentally new and quantum question, right? Which is different from how we ask something about classical compute. Now, as we start to think about quantum devices and quantum algorithms and compare it with classical, there are various vectors along which we can do this. The algorithms are fundamentally different, right? So the first question we ask is, what are these algorithms really giving us? Are they computing the same thing we would classically, but doing it faster? That's part of the answer, not all the algorithms. Speed is not necessarily always the focus. The focus with many of these algorithms has been, are there things that we want to compute using classical or quantum devices, but quantum devices fundamentally do it better because you have access to qubits, you have access to entanglement as the compute resource. Now you might say, what are these problems, right? And they range all the way from predicting new materials, molecules, which are fundamentally quantum mechanical problems, to other kinds of optimization problems that can be mapped onto such devices. So it's really a very broad spectrum, and technically, this is a really deep field because you're asking both how does something compare with a moving target? Classical compute is also a moving target, but also you're asking, what are the the limits, what are the information theoretic limits that we can accomplish on quantum devices, not just today, but 3, 5, 10 years from now.
We're sort of entering a phase now, which is exciting to think about. We're like, hey, quantum computing enters modern data centers. And that sounds like a scale up phase, right? That sounds like, oh, we're going to build capacity. What did it take to sort of get us here from something that was, theoretical that people would follow to something that has like many practical uses?
Yeah. So there has already been a tremendous amount of science, engineering, prototyping, and the initial phases were the different qubit architectures. And I want to re-emphasize this. I've said this so many times over the years. It's not which qubit will win. They will all in some way be involved in a future quantum compute world. But each of these qubits is realized using a different looking technology. So superconducting qubits are the ones that look most like classical chips, right? And superconducting as well as semiconductor based quantum technologies all leverage things that are already in existing semiconductor manufacturing. Then there are photonic quantum technologies, and there are many companies. I'm not going to name them because that becomes its own set of chaos. But there are technologies that are based entirely on photons, so all photonic schemes. Then there are technologies that are based on either trapped ions or neutral atoms, which are really deriving from a deep field of atomic, molecular, and optical physics, right? And AMO physics has been around, well, since before I have been around. And several Nobel Prizes over the years have been awarded for various advances in AMO. We are finally at a point where we can talk about entanglement, we can talk about chips that incorporate multiple of these either traps or neutral atom systems. And then there is a really exciting and new class of quantum devices, which is, of course, based on topological qubits. So each of these is a platform. You could think of these as, ways of realizing what it means to have qubits, to have an architecture, gates, etc. We have these devices. They've gone from baby devices to devices that are, ones that we want to run important problems on. So we've entered a phase of co-design where we're taking problems that are important. We have resources that are not yet perfect. They're not fully scaled up. We're not fully fault tolerant. There's no universal quantum computing yet. But we're taking these problems, co-designing them with these devices, figuring out the right problem to device fit, then thinking about how, say, in a data center that you want to build over the next 2, 3, 4 years, which is really the only horizon you can predict for some of these, you think about the problem, you think about the right mix of maybe 1 or 2 of these quantum technologies, as well as, of course, your favorite classical compute architecture, and ask, okay, what is the right mix of these? And that itself is an interesting question.
Tell me if this is a crude analogy or a decent analogy. We used to have like a few ingredients that we'd maybe go into this. We got like, I don't know, a meat, a vegetable, and a spice. But suddenly we have a lot more ingredients at our disposal. And some of these ingredients that can go into these sort of like recipes are very good at certain things we want to do. And so we have like a much broader range and and now we can design much richer, fuller dishes. Is that a decent analogy, or is that a bad analogy?
I think that's a really good analogy. And we've also added a few more things to our repertoire from the classical side, right? With very scalable AI systems becoming almost expected now everywhere. And a newer question that has come up is there the right mix, to borrow your analogy, the right set of ingredients of compute that also work towards minimizing the amount of energy use, right? So that's the bottleneck that ultimately all of these technologies run into. So I bring that up because in the early days of comparing classical and quantum computing, the only number that was talked about, and this came up a lot with some of the initial quantum advantage results, was the time to compute. So there were problems that were picked where folks said, well, this would take, 10,000 years on the biggest, baddest classical computer, but we made it happen in N days. And now folks are asking an additional question. Well, is time to compute the only metric? Could we also ask about energy to compute or resource optimization as a framework to think about such data centers in future?
How does this fit in with scaling data centers for sort of quantum applications versus like the AI juggernaut? Are they intertwined and interrelated, or are they sort of competing for attention, and AI is getting a lot of attention right now?
I think they're intertwined and entangled, if I may, particularly because quantum devices have the potential to enter these large data center concepts that are being put forward in very ambitious plans and act as either accelerants for particular pieces of the compute workflow. And eventually there would be, entire classes of algorithms. We don't have this at the moment, but we can see the path to this, where you optimally use large AI systems plus large quantum devices, and that's almost an expected workflow as opposed to something that you do in order to just accelerate a part of the calculation. So we can kind of see the path to that. And that path wasn't something that folks were talking about, 5 to 8 years ago, because this AI path wasn't as apparent. We've now seen announcements where quantum and AI are going hand in hand. And I absolutely agree. This set of technologies is essential to American competitiveness. It is essential to national security. It's essential to economic well-being, everything that we need to make happen. So I'm really excited to see the announcements and the investment in these technologies.
To understand what a qubit is, consider that classical computers, like your laptop or smartphone, use bits. That's either a 0 or a 1, like a light switch that's either on or off. On the other hand, quantum computers use qubits, which stand for quantum bits. A qubit is not only a 0 or a 1, but can also be both at the same time. That's called superposition. Because qubits can be in multiple states at once, quantum computers can process much more information at the same time compared to classical computers. This ability makes them incredibly powerful for certain types of problems, like simulating molecules, factoring large numbers, or searching huge databases. Simply put, quantum computers can try many possibilities at once, making them potentially much faster for some tasks than regular computers. What is the role of quantum in the era of AI specifically? What are the parts that each play if they're both being located in this new, super data center?
So there are problems where we can argue, we can't rigorously mathematically show, but we can conjecture that the problem itself is well mapped onto a quantum device. And that means something that itself is a quantum problem. But just to say that there is consensus that there are problems that will require quantum devices, quantum computers, and these are problems that will then be synergistic with some part of that workflow that you solve on a classical computer. And there are some efforts towards this. Actually, our colleagues and friends in the Nordics have already invested in a large NVIDIA system, plus a large quantum computing company that is going to try and demonstrate that this concept works in a scaled kind of data center environment. So, we're at a point where it's happening. It's commercial. It's not only commercial, but it's got prime time attention.
I think what is interesting about your lab and your work is that it's so multidisciplinary. And when we look at quantum computing, quantum sensing, quantum networks, we're no longer thinking about this in terms of a classical university divide would be like, oh, life sciences sits over here and physical sciences sits over there. So to talk about the interrelatedness and maybe take us through quantum computing, quantum sensing, quantum networks, and who is interested in what, because it's sort of lots of people are interested in this from many different applications and use cases?
Absolutely. I think some of the traditional divides between areas, departments in a university setting, just when it comes to quantum, that just goes all out the window. So I'll give you examples on all three. So with you know quantum algorithms, one of the applications, one of the biggest applications we anticipate will be in molecular and drug discovery. And I historically have not known anyone on the life science or pharma side of things, and had a very distant view of the work happening there, say in computational structural biology or computational neuroscience. And suddenly these folks are talking to me and saying, hey, how can your quantum algorithm do this thing? And I was like, well, this thing that I can't pronounce, if we can find a way to represent it mathematically, say as the graph theoretic problem, if we can, um, you know, use a different representation for this, then we might be able to map it onto a quantum device. And so some of these conversations start out, and it almost sounds like two people from different planets talking.
Literally, it's two languages speaking, and you have like a common word, and you're like, wait, what's that word? I recognize that word. Tell me more. What is that?
Exactly. And then we go from that to, oh, your thing looks like this class of graphs, and I know how to do something with that. And, before you know it, we're now in applied math land, and no longer talking about some problem that only has words I can't pronounce. The example I give in quantum sensing is even more immediate, right? So we have a project on sensing of bioaerosols. And bioaerosols, by the way, when you sneeze, COVID was bioaerosol, but also there are a bunch of bioaerosols that exist. We are shedding all the time from our skin. This actually creeped me out when I heard about it. And we were shedding bioaerosols everywhere. I was like, oh no, I don't want to know about that. But there are, bioaerosols all around us, and some of them carry infectious diseases. Some of them impact air quality in ways we don't yet understand. Some of these are, of interest from a national security standpoint. So we start to say, okay, well, what can quantum sensing do? And realize that, we can, by orders of magnitude, improve the sensitivity, not just with single, but also with networked quantum devices. So networked here is quantum devices that are connected via entanglement that is being used as a resource, essentially, rather than classically connecting these. And that gives you some overall sensitivity advantage in addition to the sensitivity advantage you get at each of the sensors.
For people who don't follow this close, this is like, these kind of quantum sensing is like, my understanding is unprecedented accuracy. Things that you have to be incredibly precise.
It is absolutely, the most precise measurements we can do of fundamental constants of nature, of gravity, of knowing things about the physical world have been done with quantum sensors. What we're now talking about is how do we deploy some of these quantum sensors? How do we integrate these in a way that they're also telling us something about our air quality? They're telling us something about the human body. There's some quantum sensors that we think can be used for diagnostics in the human body. I was just having a conversation with a group member who, brought up this idea that they could be used for real-time monitoring of radiation therapy. And I was like, wow, that would be an application that matters. We would want to know when somebody is undergoing a certain kind of treatment, if there's an advantage to being able to, say sense their reaction to it, to know something about their response to this kind of therapy. So these are really, I think, examples where quantum sensing, quantum computing that have historically, lived in physics, engineering, kind of very physical sciences, I guess, environments are now impacting people from entirely different disciplines. And I have conversations with biologists, with atmospheric scientists, with folks working on all kinds of life science problems because of this.
I think some of the startups you've been involved with or founded, part of your role at one level is to I think make this more accessible to scientists, other smart people in a lot of other fields. But how can you bring quantum into your toolkit so you can use it to greatly accelerate your work?
Absolutely. That in some ways captures what I've been trying to accomplish and what I hope to accomplish, which is bring quantum into people's everyday lives and have positive impact through quantum. So what we're now excited about is how do we scale quantum technologies? How do we think about scaling to get to a certain threshold where these valuable problems become open not just to researchers in the field, but to folks who are coming from outside. They want to use a regular cloud model, log on, they know which algorithms, they have a problem, something can break it down into the right set of circuits, and then they want to be able to run it, right? And there's development on all sides that needs to happen. There's development on the hardware side, there's development of new algorithms, there's co-design of these things, there's how you optimize the decomposition of the problem, how you optimize the decomposition to leverage near-term and not so near-term hardware. And then with that, how do you kind of bring in, pulse level, device level control? So various aspects of this are things that companies I'm involved with are working on. And I think it's an exciting time to be doing all things quantum.
I sort of think of it in terms of like what CRISPR has meant for gene editing technology, or precisely, cutting and modifying DNA sequences. And it wasn't like it really actually did anything that people couldn't do. It just, you needed very specialized knowledge and ability and training. And CRISPR comes along and sort of like democratizes this. There actually are high school students and college students like working on systems and can do this now. And that creates this potential revolution in how we do therapeutics and more that is, just coming to market now. It seems like it has that kind of potential if we can make these kind of platforms available.
It certainly does. And that is something that we're, hoping, not just hoping, we're actively working towards realizing. And we're starting to see some examples of it already, right? So we're starting to see major pharma, life science innovation efforts saying, okay, how do we migrate our workloads, our computational workloads onto some of these devices? And what can our teams start to do? And that's really, been a turning point for the community, because so far it was a bunch of quantum people saying we can solve these important problems and having discussions, but not yet, we weren't at a point where workload migration was happening. So I think, this is one of those fields where you wake up every morning, you see a new announcement, you think, oh my gosh, today's the day. And today could be the day, right? And it's not that unthinkable that somebody with a cool algorithm with a current device solves an open problem either in biology, mathematical science, or pick your favorite field.
One important point to realize is that there are different types of qubits, and many more ways to deploy them than just the use of semiconductors in traditional computing. For instance, Ignacio Cirac and Peter Zoller demonstrated in 1995 how logic operations could be performed by ions held still in invisible electric traps with lasers to control them. The most prevalent qubit type is a superconducting qubit, tiny electric circuits chilled to temperatures colder than outer space. There are also qubits made with particles of light called photons that travel very fast and can move easily over long distances. Spin qubits, topological qubits, neural atom qubits. These are all additional types rooted in physics. The key here is that these exotic setups increase the demand for data center facilities to house them, which others can more easily benefit from as quantum computing as a service becomes available in the cloud. How does this result in, quantum internet in your home in some period of time? Or how does this actually impact something that, aside from amazing scientific discoveries, of course that has enormous impact, but like daily impact in our lives for someone who doesn't work in science research and discovery?
Totally. Okay. So when we think about networking of quantum devices or networking of quantum sensors, we're really talking about sharing entanglement across a network. And this network looks very similar in some ways, but very different in other ways from classical networks. The similarities as far as, what the field is working on, we want it to all be telecom. so that we can find ourselves in a scenario where existing fiber or fiber that looks like existing fiber can bring the quantum internet to your home. There are a few things that are different, right? So the layering of such a network doesn't look the same. The quantum version of SDN, software-defined networking, looks a little bit different. And of course, even in classical networking, no one's talking about SDN anymore. So there's really a fairly kind of deep set of things that need to happen in order to scale some of these quantum networks. But we can do these on a small scale, right? So we can do small metropolitan scale. I want to say the LA area is perhaps a stress test of this metropolitan scale, but folks have demonstrated networks in various parts, Chicago being a good example, New York being another example, Boston, where you can deploy these networks. Now, the question is, what are you running on top of the network, and how does it coexist with the classical network? And what does this entanglement deliver to your home? Say, let's call it entanglement as a service. What's that going to do for you? And there's some examples. We, of course, have heard a lot about examples in secure communication, ultra secure, physics-based security, goes by various names. But then there are other things that we haven't yet envisioned or unlocked that would leverage such networks. I always kind of give the example when folks were first bringing the internet to your home, they probably didn't have Airbnb or Instagram in mind, right? Those were not applications that were apparent to us. So we don't know what some of those farther term applications of these networks will look like, but we have near term applications that are so valuable, it's worth doing regardless.
When I think of what are sort of applications or use cases that just kind of accelerate the field or the state of the art, the technology, or bring widespread interest or adoption, I feel like I've heard the most of over the years of just quantum computing and the effect on cybersecurity and the counter response to quantum computers that can break every bank algorithm. Is that true where you see a lot of interest, or is it just that's what I hear shouted loudly?
A bit of both. So the good news is that there's a two-pronged approach that's being pursued to post-quantum cryptography. One is algorithms that are actually in this PQC domain, and that's important. And it's going to be a game of cat and mouse. The algorithm is released, somebody breaks, and that's happening. And there's an effort from NIST and other federal agencies to kind of do that. The second is using quantum networks themselves to secure some of the data, and that could help with threats that folks talk a lot about at these conferences, things like harvest now, decrypt later, et cetera. Those could then be protected via quantum networks. So this two-pronged strategy, I'd say, kind of all goes hand in hand, right? We want to work on new algorithms. We also want to realize this physics-based security. And as the kids say, why not both? So we should certainly keep an eye on both. And I'm really glad that investment in both of these directions is being made.
To put our investor hats on again, day job, I'm a venture capitalist, Deep Venture Partners. What are some of these sort of opportunities, things to look for, sectors and subsectors that are worth paying attention to, all related to kind of the three you mentioned, quantum computing, quantum sensing, quantum networks, or something totally different?
Yeah. So investor hat on, there is it's a lot that's happening at the interface of compute and network. And I would say that that's where companies that are either being announced or entering into that domain. We've heard of certain companies that come from classical networks actually jumping into the fray there. Those are ones that I'd really keep an eye on. For quantum sensing, there are companies that look more like a traditional defense or space-based play that are being announced, but their core technology is a quantum sensor-based platform. So I'd say that those are areas to keep an eye on. And of course, some of our quantum computing companies are getting to a point where they're entering kind of those really large institutional investments. We've seen a couple of companies go public, so that remains a vibrant, growing ecosystem.
And do you think like these big companies and, that you're probably, I think, referring to the, whatever, Google's, Microsoft's, Amazon's, IBM's, Intel's,
Right.
NVIDIA's of the world, devoting a lot
Yep.
of resources to this. Like,
Yes.
is this a field? I mean, do you think that it demands the resources of one of these kind of, big, giant companies that can put a lot of resources and engineers and scientists and do this? Or is it, a small group of people in a room that just have a novel approach who, and are going to win out? And I think there's, AI is a great parallel because like everyone said, it's the former. Oh, it's all that you need to have these massive computing centers. And then some little teams from China come along and everyone says, oh, we can do a lot with a lot less. And then it turns it on its head. So what do you think for this field?
This field, I'll say that the traditional path to scale that leverages semiconductor manufacturing, that does all of the things that we already know, that lends itself to big investment from these companies. And that's why we're seeing announcements from each of these companies. Any of their earnings calls comes up. But some of the really innovative, crazy stuff that's shown great promise over the last 3 to 5 years has come from some of the startups in this field. And you see that the larger companies are partnering with those startups. They're taking this very gentle approach to saying, okay, you have a new qubit or algorithm. We don't want to assume that that's something that our internal team could have done anyway. So we've seen that with some of the atomic platforms. We've seen that with the trapped ion platforms and with the photonic play. So it's not obvious to me that the that the only way for this to happen is as a big company, because each of the companies you just listed were once that small disruptor as well. So I
Sure.
wouldn't rule out the that approach, but yeah, it's something that does require a lot of investment upfront, particularly the quantum computing side of things. So you'll see less and less that a university lab tries to build the quantum computer. There's a lot of engineering, a lot of tech design, a lot of other stuff that's going on that lends itself better to either being in a company, a large company environment, or certainly an established, well-funded startup. Yeah.
To wrap up, I'd love your perspective on like just the university environment now, spin-off companies commercializing things versus like how do someone like yourself, I mean, you have your hand in a lot of different things. We haven't even talked about the US science envoy part. We can, but how does it like, in terms of like advancing this through commercialization, like who are the kind of like scientists that should be in academia? Who are the types that should commercialize? Are you recruiting like star grad students to go, take forth and set forth and run these companies? How does it work best?
All of the above. So a lot of the younger talent entering this field, students, postdocs, they're coming in with a very, um, you know, they want to do stuff that really has impact, and they're not limited by, hey, I want to go into academia or I want to go work for a large company. They're like, I want to do something in quantum that matters. And that could be, if there's IP that's generated out of their thesis and they want to start a company. Yes. I'm like, I will be right there with you, whatever capacity I can be helpful. There are scenarios where folks say, hey, I want to go spend 6 months with the team at pick your favorite company and contribute to this part of the development. And, I'm like, okay, absolutely, you should do that. So this is one of those fields where the boundary between industry, national labs, academia is very is blurred, is porous, and that's a very good thing. That certainly wasn't the case in physics, chemistry departments. So, more traditional departments that would live typically in the College of Letters and Science. They would, not have a tech forward approach. Now, if you talk to electrical engineering department, always there were, the ones who were starting companies, commercializing tech, and that existed. And that was one of the reasons why back in the day when I was a grad student, I was like learning from my thesis advisor who had the same kind of, porous kind of, so he works in photonics, and in photonics, there's always been, set of applications and companies that have come out of his lab. So I kind of learned a bit of that, and I think I'm really seeing a lot of my traditional quantum colleagues embrace that attitude. So it's fun.
As an appointed U.S. science envoy, which my understanding of the role is that, this is from the State Department. You're meant to build partnerships with other countries, building quantum programs. Is this? Are we at a cooperative, for lack of a better term, a kind of kumbaya phase in the world where we're all going to work together, or this can change quickly and become ultra competitive, or are we in that, and are we like competing and partnering at the same time? Where are we in sort of the international development of this?
All of the above again. So we have, over the years, the U.S. has signed a set of science and technology agreements, signed a set of joint statements on quantum science and technology with specific countries, bilateral agreements. And those are all recognizing that science is and has been a global enterprise. At the same time, there's this delicate dance that this is a sensitive and a critical technology, and we can't ignore the national security implications, right? So even working on fundamental research, we kind of have to think about that. And my role has been really both to communicate and talk about the exciting work, establish these relationships, and demonstrate that, American leadership in this area is really, really important. We're there. We have some of the best scientists in the world. And we also want to work with some of the best scientists and technologists in areas with like-minded allies.
Final question is, if you, I guess in one of these many roles or hats that you wear, were given a magic wand and could do one thing to advance this field, our development, its applications, its people's understanding of the importance, what would you use your magic wand on? What would you use it, the single thing that you would want to solve or advance?
I think the single thing would be for everyone, particularly non-scientists, to realize that this is a technology to invest in because it will better their lives. And I think that if that message could, be conveyed, if that's something that, folks could be on board with, that would be amazing. And I frequently talk with folks. I want folks to be convinced that this is, yes, a technology where the words are hard to pronounce, the concepts are not particularly easy to follow, but regardless of who you are, this is a technology that will touch your life and it will do it for the better. Therefore, an investment is valuable. So, magic wand.
And will the quantum revolution mirror be just as impactful as the original sort of computer revolution?
In my mind and in my imagination, more so, because it's adding to that. And this is something I'm mindful of, that we want to make sure we communicate that impact, we communicate that of this technology.
Prineha Narang, professor in physical sciences and electrical and computer engineering. It's a mouthful. It's a lot of words because it's so important at UCLA. Thank you so much for joining us on Deep.
Thank you. Thanks for having me here.
This episode has been brought to you by Deep Venture Partners, an emerging venture capital fund in Silicon Valley. Get show notes, transcripts, helpful links, and more at deepvp.com.